Hey everyone, welcome to The Explainer. Today we're diving straight into the hidden mechanics of the physical world. We're going to take our basic understanding of simple mixtures and level it up to master some seriously incredible separation techniques. I mean, the world around us is literally one giant mixed-up puzzle, but together, we're going to untangle the whole shebang.
To kick things off, just think about a really everyday transformation. How exactly do we get those perfectly white, geometric crystals of sugar from, well, tall, fibrous, green sugarcane plants? It's kind of wild when you think about it, right? The secret lies in the highly practical, honestly fascinating science of separating mixtures. And that's exactly what we're decoding today.
Okay, let's dive into our roadmap. First, we'll classify our mixed-up world. Then, we'll hit the math behind the mixture. After that, it's solubility and pushing the limits, followed by crystallization, which is basically nature's purification. And we'll wrap it all up with distillation, boiling, for purity.
So, part 1. Classifying our mixed-up world.
Before we can separate anything, we have to know what we're dealing with, right? It basically boils down to two main categories. First up, we've got homogeneous mixtures, or solutions, which have a totally uniform composition. Think of sugar, completely dissolved in a glass of water. The sugar just hides perfectly within the liquid, like magic. On the flip side, we have heterogeneous mixtures. These have a non-uniform composition. If you stir sand into water, the particles stay completely visible and eventually just settle to the bottom. So short version, homogeneous hides its ingredients, while heterogeneous shows them off. We can actually test this visually. If you shine a laser pointer directly through a clear salt and water solution, which is our homogeneous mixture, you can't even see the laser beam traveling through the liquid. The salt is dissolved so flawlessly, so uniformly that it doesn't scatter the light at all. It just passes right through, almost invisibly.
But check out the contrast here. If you mix just a few drops of milk into that water, you've suddenly got a heterogeneous mixture. Those tiny suspended milk particles don't dissolve uniformly. Instead, they float around and actually physically scatter the light. And boom, the laser beam lights right up, becoming brightly visible as it passes through. It's a brilliant way to actually see the difference.
Moving right along to Section 2, the math behind the mixture.
Now, getting a mixture right isn't just a fun lab trick. Sometimes it's literally a matter of life and death. Take the incredible story of Dr. Dilip Mahalanobis, an Indian pediatrician. He developed a treatment for severe dehydration caused by diseases like cholera. And the craziest part? His solution wasn't some complex new pharmaceutical. It was simply the oral rehydration solution, or ORS. By figuring out the exact right proportion of salt and sugar dissolved in a fixed amount of water, he absolutely revolutionized medicine. You see, you can't just throw random handfuls of salt and sugar into a cup. The specific, calculated concentration is the key that allows the human body to actually absorb those life-saving fluids. Thanks to this precise mixture, which was later popularized by the WHO, millions of lives have been saved, literally millions.
To calculate those perfect concentrations, we rely on three vital formulas, depending on the state of the matter we're working with. First, there's the mass by mass percentage. This one is perfect for solid mixtures and packaged foods. Second is the mass by volume percentage. This is an absolute must in medicine and lab work, mostly because pouring a liquid is just way easier than trying to weigh it. And finally, volume by volume percentage. You'd use this for mixing two liquids together, like diluting agricultural pesticide sprays, where getting the precision right protects the soil. And what's really interesting is that these seemingly abstract math formulas are living right inside your house right now. Check the back of a milk powder packet. It uses mass by mass percentages to detail the exact protein and sugar content. Meanwhile, a life-saving glucose IV drip at the hospital relies on mass by volume. A label that says 5% W/V guarantees there are exactly 5 grams of glucose in every 100 milliliters. It's perfectly calibrated for a patient's bloodstream. It's just everyday math doing the heavy lifting.
All right, Section 3, solubility, pushing the limits.
So here's the thing about solvents. A solvent, like a plain old glass of water, is not a bottomless pit. It has a strict maximum holding capacity for whatever you're trying to dissolve into it. When a solution hits that wall and physically cannot dissolve even one single more grain of solute at a given temperature, it efficiently becomes what we call a saturated solution. If you try to add any extra solute after that point, it's just going to sink right to the bottom, totally untouched.
But if you want to cheat this system a little bit, heat completely changes the rules. The solubility of a substance isn't totally fixed. Say you heat up a saturated solution of sugar water on your stove. Well, the hot water physically stretches its capacity, allowing it to hold way more sugar than it could at room temperature. Although, quick side note, for gases dissolved in liquids, it's the exact opposite. Increasing the heat actually decreases their solubility, which forces the gas to bubble right out. Which brings us to Section 4, Crystallization, Nature's Purification.
Crystallization is this amazing way we can separate a pure solid from a solution, and it relies entirely on the rules of heat and solubility we just talked about. Here's how it goes down. Step 1. You heat your solvent and cram it absolutely full of a solute until it is totally saturated. Step 2. Quickly filter that hot solution to get rid of any undissolved, unwanted impurities. Step 3. You just let the solution cool down. And Step 4. As that liquid cools, its capacity to hold the solute shrinks back down. It just can't hold all that dissolved solid anymore, so the excess material physically separates out as pure, solid crystals.
If you want the absolute best results here, patience is key. The real secret to perfection is in the cooling. If you take that hot, saturated solution and, say, plunge it straight into ice water to cool it rapidly, you're going to force the solid out way too fast. You'll just end up with tiny, poorly formed grains. But if you let it cool slowly and undisturbed at room temperature, you give the particles the time they need to come together perfectly. This slow cooling builds much larger, shiny, completely pure geometric shapes. It's basically nature's very own purification system.
And finally, Section 5, Distillation, boiling for purity.
Distillation is our most dramatic technique. It allows us to separate a homogeneous mixture of miscible liquids, liquids that mix together flawlessly, by taking advantage of their distinct boiling points. The logic here is just brilliant. First, you heat the liquid mixture. Because the liquids have different boiling points, and ideally you want them separated by at least 25 degrees Celsius, the liquid with the lower boiling point turns into vapor first, leaving the other liquid behind. Then you pass that hot vapor through a cold condenser tube. The cooling turns the vapor right back into a liquid, and you simply collect this pure, condensed liquid in a completely separate container. When you trace the physical journey of a standard distillation setup, you really see how elegant this whole process is. The heat source warms the mixture in the boiling flask. Then, as the lighter liquid becomes a gas, it travels up and gets pushed into the angled condenser tube. That tube is surrounded by a jacket of flowing cold water, so that hot vapor is instantly condensed back into liquid droplets, dripping right into the collection beaker as a perfectly pure substance.
Now, you might think distillation is just dry, boring lab work, but it's actually been a profound sensory art form for centuries. There's a town in Uttar Pradesh, India, called Kannauj. It's known as the perfume capital of India. They use this beautiful traditional distillation method called Deg Bapka. Get this, they literally extract that incredible earthy smell that rises from the ground after the very first rain. By distilling clay and capturing the aromatic vapors, they condense the actual essence of rain into a world-famous natural perfume called Mitika Itar. I mean, no way, right? It is an ancient, completely beautiful application of the exact same science we just explored.
So, what does this all mean? Think about the incredible range of things we've covered today. From Dr. Mahalanobis using precise concentration math for life-saving IV drips, all the way to artisans distilling the literal scent of the earth into a tiny bottle. The science of separating mixtures allows us to isolate exactly what we need to survive, to build, and to create. So I'll leave you with this. As you look closely at the mixed-up world around you today, what other hidden treasures could we extract if we just applied the right technique? Thanks for hanging out with me for this explainer. See you next time.